So, good evening, everyone. Um, so we will be starting our problem solving and doubt clearing session. So, I'm Calvin Joseph, and I'm from IIT Kharagpur, and I'm a PhD scholar over here in the second year. So, I'll be conducting your problem solving and doubt clearing session for the week three questions. And week three parts, we'll be solving some sums so that you can get any understanding of you'll get understanding of it. Also, so today we'll be focusing on differential equations, and I will start sharing my screen. So is my screen visible?
Yes.
Okay. So let's start. Okay. So this is for week three, and we will be studying differential equations today. So can anyone tell me why do differential equations come across in electrical circuits?
To solve for current equations.
Yes, to solve for the equations we need it. So I'd like this session to be interactive. So you guys should ask me doubts and queries which you have. Okay. When I'm solving something, also you can stop me and ask me if you have not understood any step, or if something is not clear or something is not visible. Hmm. Okay, so you can do that. There's no doubt of it. And whatever doubts you have, you let me know. So we have, so there is a differential equation. So in the circuits which you will be solving currently, they will be linear. It will be linear differential equations you will be solving. Okay. So can you tell me, for an inductor, what is the relationship between your inductor voltage and your inductor current? Sorry. What is the relationship between your inductor voltage and your inductor current? So the voltage across the inductor is given by VL is L into DIL by dt. So why is this happening is because the inductor is an energy storage. It will store the energy in its magnetic field. Okay. And because of that, there's this differential equation is formed. Similarly, for a capacitor, if you will see, consider this your capacitor, this is a current flowing in, and this is your voltage across the capacitor. So the current flowing into the capacitor is given by C into dVc by dt. Okay, so this inductor and capacitor is what results in the energy storage elements in your circuit. So it is good. It is not like we don't need energy storage circuits, they're bad or good. It is required. They have applications. And so we have to learn how to analyze circuits which have these things. So what happens when you have your inductor and capacitor, they come in your network, it gives rise to a differential equation. So let us assume over here, this is your resistor, this is your capacitor, which is connected over here, and this is your voltage source. Okay, your voltage source. So when you try solving KVL or KCL for this equation, you will, okay, we will solve KVL for this. So can anyone tell what will happen if I apply KVL over here? Assume the current is IC. Assume the current is I. Okay. So can anyone tell me what will be KVL over here?
Vs minus R into I.
Okay. So I'll go from here. So this is Vs then it will be minus r into
All
I.
right.
Then assume this is
So again,
minus VC.
C integral of
Hmm?
C integral of dA will be
Just one minute. Okay?
1 by c integral of
Okay. Yeah. Yes, you were saying.
1 by c integral of di by dt.
Okay. So you are saying 1 by c integral of di by dt. Okay. And this is equal to 0. So there should be a minus sign here, right? So this will be, if you do KVL, it will be Vs minus R into I minus 1 by C integral of di by dt. Hmm. Okay. So this is one differential equation. So what happens is when you are learning, you are going to learn about electrical networks. You're learning about the circuit theory, and then you see all these complex equation. What happens is you get like fear, you get become afraid, like these are so complex and everything. So yes, differential equations are difficult, and it takes time, it takes practice to understand, but you must look into the circuit properly, and you must properly write the mathematical equations. All right, it is difficult, I admit, but if you do it correctly, if you do it step by step, then it will be easy. So now we have written an equation, and in this equation, what it is, it a differential equation? Is this equation which we have written, is it a differential equation? Okay, so it is an integral differential equation, like it has integration and differentiation as well. So what I don't want, I don't know how to solve such equations which have integration as well. Like currently we will try to avoid such things. So what I want to do is I want to get rid of my integral term. Okay. Now I know that, yes, someone is saying something. Okay. So what do I know? I have written KVL over here, and now I have got this equation. So then I stop. I don't know how to proceed. Now you look at your capacitor. Your capacitor is your energy storage element. And what is the current flowing through the capacitor? Mhm. If you see, the current which is flowing through the capacitor is your I. So your capacitor current IC is equal to your I. Okay, that is my capacitor current. Now I have one more information. I know that the current through my capacitor is given by this equation. So I know my I is given by, is equal to C into dVC upon dt. Okay. So I consider the equations of my capacitor and I write it in this form. Now I substitute this in this equation. So wherever I is there, I substitute it by C into dVC by dt. So what will happen is it will be Vs minus R, and I is there, so I substitute by C into dVC by dt. So Vs minus R C dVC upon dt minus 1 by C. Okay, now it is integration of d of dt into C. No, sorry, here it is not this, right? Okay, there's a mistake over here. This will be actually this is 1 by C integration of IC into dt. Okay, because from here, if we can write it as, this can be written as voltage across the capacitor can be written as 1 by C integration of IC into dt. Okay, so that is over here. So where IC is, there is my I. So I will write it as minus 1 by C integration of what is I? C into dVc by dt. So C into dVc by dt, this is equal to 0. And dt also is here, so this is dt. So is this point clear or someone has doubts in this?
Yes.
Okay. So now I've got this. So what, let me, it's not written properly. 1 minute. Okay. Move to this. So this is into dt is equal to 0. So how will I proceed? So what I will do is, I will cut this. I cut this and I cut this. Okay, they get cut. My C and C also, they get cancelled. So effectively I get, go down. It is my Vs minus Rc into dVc by dt minus integration of dVc is equal to 0. Okay. So that I write it further as integration of dVc. Integration of dVc is equal to Vc. So like, integration is the opposite, of differentiation. Okay. So when I do integration and differentiation of it, it just comes out to be Vc. So it becomes Vs minus Rc dVc by dt minus Vc is equal to 0. Okay. So till here, is there any doubts?
No.
Okay. So I have done all these steps. Okay. That's taken me so much of time to figure out. So what I prefer to do is, instead of writing it in this form, okay, instead of writing in this integral form, I avoid that. And how do I avoid that is, for a capacitor, I will write the voltage across it as Vc. Okay. And for an inductor, I will consider the inductor current. So whatever I do, when I do KVL or when I do KCL, I will write the voltage, or I will write the equations for the capacitor or inductor. Okay, let me go one by one. So, what is my tip? Okay, tip. When you're solving this is, consider for a capacitor, you write equations considering the voltage of the capacitor. Okay, write equations considering the voltage of the capacitor. And in case it is an inductor, you write equations considering the current to the inductor. Don't write equations for a capacitor in terms of the current flowing in the capacitor. Don't do that. Similarly, for an inductor, so this is not correct. This is the preferred way. Similarly, for an inductor, you don't write equation in terms of the voltage across the inductor. You avoid that. You preferably write equations for an inductor based on the inductor current, and for a capacitor, you write it based on the capacitor voltage. Okay, so then these sort of integration, extra things would be avoided. As much as possible, it will get avoided if you follow this convention. Okay, so are you guys still here, or is it like, okay? So let me again, so I will recap what we have done. We have written the equations for an RC circuit. So there was an RC circuit, and we have applied KVL over there, and we have come to the conclusion that it is easier that because there's a capacitor, you write the equations in terms of the voltage across the capacitor. Then you get this equation. So what is the order of this differential equation? What is the order of this differential equation? Who will tell me?
First order.
First order. Okay. So this is a first order differential equation. Why? Because there's a single derivative. Okay, there's a single derivative. This is just the first derivative is there. If there is the second derivative, then it becomes a second order system. Another thing which in most circuits it happens is the order of the differential equation is equal to the number of energy storage elements. So in this RC circuit, there was only one energy storage element. So that's why the order of the differential equation comes 1. Okay. So the order of differential equation is mostly, in most cases, same as the number of energy storage elements. Okay. So I'm going to add one more page. Okay. All right. So that we have considered for a first order system. Now let me write down a second order system. Okay, we will go for a second order system. So this is my second order system. All right. So what I will do is I will write the voltage across the capacitor. I will denote it by VC. I will denote the current through the inductor by IL. And then I will write the equations. Okay. So can anyone tell me what is the what you say? Can can you apply KVL and what will you get when we apply KVL?
Vs is equal to
Okay, Vs is equal to
IL into R
IL into R. Okay,
plus L into di by dt
L into DIL by dt. Okay,
C into dvc by dt.
1 by C.
okay, you're saying 1 by C integration of IL into dt.
IL of
Okay, because this actually is your voltage across your capacitor. Okay, so is this a first order or second order? Or like, okay, so what is the order of this equation?
Second order.
But there's no d2 by d2t. This is not there.
But if we differentiate the entire equation, then integration gets cancelled and differentiation becomes double differentiation.
Okay, so what we have to do is we have to differentiate. Okay, we have to derive, we have to sorry, we have to differentiate with respect to time. Okay, so I will differentiate now. Okay, let me check who are the students here. So Amit Akivar. Okay, what is d of dt of Vs? What is that? What is the derivative of Vs?
0.
Okay, that will be 0. So d of dt of Vs is 0. Then what is, so okay, what is d of dt of IL into R?
0.
R DIL by dt.
So if I have di dt of IL into R, since R is a constant, it comes out. So it becomes R into DIL by dt. Okay. Similarly, if I do d of dt of L into DIL by dt, it comes out to be, because L is a constant, it comes out, so it becomes L. Then derivative of one derivative, it becomes second order derivative, so it becomes d2 IL upon dt2. Okay. Now is the thing is I have to also do d of dt 1 by c integration of IL into dt. Okay. So this, the derivative and the integration, they cancel out each other. So I will get, effectively I will get 1 by c into I into L. Okay. So any queries in this part?
First thing is, I have a question related to this.
Uh-huh.
You know, since we are applying DC, so IL would be sometime it would be like saturated, like steady state, right? In steady state, IL would be constant.
That see, this equation is valid. This equation is valid in steady state as well as in transient. So we have written the overall equation. Okay. In
Okay.
in steady state, finally what will happen? The capacitor will be charged to Vs and inductor current will go to 0. But that does not mean it is always like that. When you turn on the voltage or when you apply the voltage, initially the current was 0, voltage also was 0. So it will have some dynamics. So that dynamics of that is written by this equation.
Okay, so the transients we are finding out.
Yes, yes. The differential equations show you, they help you in solving the transient. Okay, and it is also, now in this circuit it is DC, but suppose it was not DC, it was AC. When AC is there, then these parts will not die out in steady state. They will also be there in steady state also.
Yeah, that makes sense. So that is the question actually. So VS would be steady state for after some time. So that's why I'm asking the question.
Okay, okay, yes.
So it's a generic voltage source. We are deriving all these equations. If it is a generic,
No, no,
it is
no.
not a DC or something. Yeah.
Even if VS is a DC voltage source as well, it is not that you apply this DC voltage source, immediately your capacitor will be charged to VS. It will take some time. Okay, suppose this was open. Assume it was open. Assume there's a switch. Okay.
Yeah, I understand. I understand that point.
So if I just close it, immediately my current will not go to 0. This will not get charged. There will be some dynamics. And those dynamics
Yeah,
are...
my point is different actually. I'm looking at the system level. When we turn on the system itself, it will get settled by some time. After
Yeah.
that, our functionality will start. So in that direction, I'm thinking. Okay, no problem. Yeah, I
Mhm.
understand now.
Yeah, yeah. Okay. Yeah. So any other queries? Okay. So now what have we got? Effectively, when we apply it to this equation, we get 0 is equal to R into DIL upon dt plus L into d2IL upon d2t plus 1 by C into IL. So let me rewrite it properly. We get L into d2IL upon d2t plus R into DIL by dt plus 1 by C into IL is equal to 0. Okay. So this is the second order differential equation I have got. So, now I have got the differential equations I have got. Okay, I have applied KVL, I have used suitable notation, I have made all that effort I have done. Now I need to solve it. So how will I solve it? So who will tell me? Akash, Appala Naidu, Bhavana, Kavya, Amit, Bharat, all of you are there. How will you solve differential equations?
Actually, we have to divide the entire equation by L and then solve it using the differential equations. Like if we take the coefficient of di by dt as p and the constant term as q, then we'll have one formula like yc, complementary function, and particular integral, that type of solutions.
Okay. One minute. I'll go step by step what you told. You divide by L. So you get d2IL
Yeah.
on d2t plus R by L dIL by dt plus 1 by LC into IL is equal to 0. Okay.
Yes.
And how you proceed?
Next, this equation will be of form. Uh, oh, sorry. Whatever I have told, that is for first order differential equation. I don't think that will be applicable here.
Yes, it is not.
Okay. Yeah.
Okay, so that's fine. So we will go to a generic method. Okay, we will go through a generic method to solve differential equations. Okay, that use case which you told dy by dx plus py equal to q, that is only valid for first order. So
Yes, I get it.
for first order systems, we have questions of first order and that you can use. But if it becomes second order or third order, then how do we handle such questions? Okay, so we will look into that. So assume, so look at this differential equation. It is a second order differential equation. So I will write it down as, assume instead of IL, I replace IL by value y. Okay, just value y. So it will, and this R by L, 1 by LC, I just replace it by some constant. So I make it of the form d2y upon d2t plus, assume some a, plus, or no, let me write it a1. So a1 dy by d2 dt plus a2 into y is equal to 0. Okay, is equal to 0. So now what is a simple method, or what is the way they do is they replace this d by dt. Okay, this d by dt is actually an operator. Okay, it is a differential operator. So this d by dt, you replace it by some capital D. Okay, some capital D. So what does my capital D mean? A capital D means it is equivalent to d by dt. It is equivalent to the time derivative of that variable. Okay, these are a bit complicated mathematical terms, but just bear along. Okay. So what I do is I write it down as, so if I say d by dt is d, then d2 is equal to d2 by d second derivative with respect to time. It is the second derivative with respect to time. So I will write this as d2y plus a1 dy plus a2 into y is equal to 0. Okay. So can anyone tell me what is the advantage of doing this? What is the advantage? What is the advantage?
Write that
This
auxiliary form
becomes
of
a quadratic
equation.
equation.
Yes. So it So this was a differential equation, okay? This was a differential equation, this d by dt something. But now I've just got it in the form of a quadratic equation. So it becomes d square plus a1 into d plus a2 into y is equal to 0. Okay. So from a differential equation, I have reduced it into the form, it is still a differential equation, but I have written it into the form of an algebraic equation, not algebraic, algebraic equation. So it is an algebraic equation. Okay, so I have done this. Now how will I proceed? So I have got it into this form. Now you will write, this is your auxiliary equation. Someone was saying this d2 plus a1d plus a2 equal to 0. This is your auxiliary equation. Okay. So you find the factors of it. Okay, you find the factors of it. What do you mean factorize this? Suppose, let us just take some numbers. Numbers are easier. So we will write it as d square plus 9d plus 18 is equal to 0. Okay. Can you tell me the factors of this equation?
So 6 or 3?
-3 and -6.
Okay.
-3.
It's d plus 3d
So 6, 3 is also a roots of the equation.
-6 -3.
Okay. Actually, I'm hearing some things. Okay. So I write it as, there's some noise, right? Where's the noise coming from? Okay, fine. So it is written as d plus 3 into d plus 6 is equal to 0. Okay. So these are the things, and your roots are d is equal to -3 and d is equal to -6. Okay. So if when you, so because these are your roots and they are different from each other, you can write down your solution. Your y will be equal to some, let us say, some b1 e raised to -3t plus b2 e raised to -6t. All right. So we will go over again. So what I have done first, I have told you guys that I have some differential equation. Okay, we have considered second order because it is simple and easy, and I want you to understand the steps. So I replace the operator, time derivative operator, by d. Okay, by d. Then what I do is I replace the derivatives with respect to time by using this d operator. So it becomes d square y plus a1 into dy plus a2 into y is equal to 0. Then, so my differential equation has been converted into an algebraic equation using this mathematical operator. So it becomes d square plus a1 d plus a2 into y is equal to 0. So this entire, so this, so this part which is in this bracket, that is my auxiliary equation. Okay, it is my auxiliary equation. So then I will solve that. I've given some random numbers so that you can relate to it more better. Then it becomes d plus 3 into d plus 6 is equal to 0. So my roots are -3 and -6. These are my roots. So then the solution of that will be some factor b1 into e raised to -3t plus b2 into e raised to -6t. Okay. Now you will ask me, like, we have solved it, but we don't know what is b1, we don't know what is b2. How will we get those values? That should be a question which should come into your minds. I have solved it, I've factorized it, then I've written it in this form, but again I've got two unknowns which I don't know. So who will tell me how can I find out B1 and B2?
Initial conditions we can apply.
Okay, so you can apply that, you can apply initial conditions is there.
Final maybe.
Also final conditions also could be possible for you to know. Okay, so these things you will use. Okay, these things you will use. So when you actually are solving an electrical circuit, like in the ones which you will do in the examples, you are writing the differential equations. You should, from the circuit, you must determine what are the initial conditions, what are the final conditions, and then you must solve this. And then you solve the differential equations, then you substitute those conditions, and then you get the values of B1, B2, etc. And then you can proceed. Okay. Then you get your solution. So it is a bit tedious, I agree. There's an easier method, which is Laplace, which you will learn later. But you must first understand this method so that you can, fully appreciate the power of Laplace transform. Right? Okay. Okay. So we have solved one uh, one differential equation. We have solved it. Okay. We have done it. But this was only possible because there was a zero over here. Okay. Because there was a zero over here, that is why we were able to solve it. Assume it is not zero. Okay, if it was not zero, if it was d2y plus a1 dy plus a2y is equal to some function, equal to some function of t. Okay, or to not complicate it. Okay, it is a function of t. So is this clear? Like, what is a function of t? Like, if this is a doubt, I will clarify it further. So a function of t, okay, a function of t could be a constant. It can be a constant. Okay, so it could be a constant value of 1 or 2 or a something, some constant value. Function of t can also be it could also be sine t or sine of 10t. It could also be 2t square, etc. So this f of t is some function. Okay, so initially we had solved d2y plus a1 dy plus a2y is equal to 0. We solved it. Now instead of 0, there is f of t over here. Okay, there's some f of t and it is a function of t. What does it mean it is a function of t? It means it only depends on t. It doesn't depend on y. Means it is not dependent on y. So there should not be a factor of y over here. Okay, there should not be a factor of y. So that you must take into account while solving this example sums. I will show it. Okay, that I will let you know. So now in this case, there is f of t is there. Okay, this f of t is also known as your forcing function. It is some sort of forcing function. All right. So to solve this, your solution, your y of t, your solution of your differential equation will have two parts. One is the natural response, which is dependent on your initial conditions, and one is your forced response. Okay, there's a natural response and there is a forced response. All right. So what we had found here, this is my natural response. Why is this my natural response? Because this is 0. It is just 0. That is, there's no external function, external input applied. When there is an external input applied, it will have two parts. There's a natural response will come and the forced response also will come. So how to calculate the natural response? I have already showed it to you. Okay. Now we will try to understand how to calculate the forced response. So what will happen is, if I want to calculate the forced response, I will have to write it in the form of 1 upon whatever is my auxiliary equation. My auxiliary equation, I have to write it as 1 upon this d square plus a1d plus a2 into my function of t, all right? So I will demonstrate with two examples. Okay, with two examples we will proceed. Consider my function of t is just a constant with a value of 10. Okay, value 10. Simple, right? Just a value of 10. Now we will use our previous example. So why we will use this? What was the value? 9 plus 18, right? 9 plus 18. So this is y f of t is 1 upon d square plus 9d plus 18 into 10. Okay. Now what do we do? So we first factorize it. This comes out to be 1 upon d plus 3 into d plus 6 into 10. Okay, this is not my end solution because it is this differentiation still is there. And because this is in a denominator, it effectively gets converted into integration. Okay, so this is difficult to understand. It will take time, it will take lots of practice, but this is a part of network analysis. So let us go step by step. So first I will solve for this. So my y f of t, I will leave this d plus 3 over here as it is. Okay, then I will write this as e raised to 6t integration of e raised to minus 6t into 10 into dt. Okay, is there any doubt in this? Okay, sorry. Actually, it will be e raised to minus 60 into e raised to plus 60, whatever sign is here. Okay, so your d, your d is a derivative. Okay, your d is a derivative. But, and your 1 by d is actually your integration with respect to dt. So, your 1 by d plus some value 6, okay, 1 by, it actually is equal to e raised to minus 60 into e raised to 60 into dt. This is a mathematical representation of it. Is there any query in this part? Because this is the interesting thing where maths comes in. Okay. So, is this clear or are there doubts? Okay. So I'll proceed. Yeah, we'll solve. So once I solve, you will know, you will gain confidence how to solve the sums. Okay. So what I get is, this is yf of t. What is this integration? This is 1 by d plus 3 into e raised to minus 60. What is integration of e raised to 60 into 10? What is that?
10 into e raised to 60 by 60.
So it becomes 10 e raised to 60 by 6. Okay, by 6. Okay, so I've got this value. So what I do finally, I will write it as 1 by d plus 3 into 10 by 6 is here. What is e raised to minus 60 into e raised to 60?
1.
Okay, it is 1. So actually it is e raised to t 6 minus 6 because they're in the powers. Okay, and t is common. So it actually is 1 by d plus 3 into 10 upon 6 into e raised to t into 0. So 0 into t is 0. And anything raised to 0 is 1. So it becomes 1 upon d plus 3 into 10 upon 6 into 1. Okay. So we have solved so much. Okay. We have done. Now we just do the same for this part. So this we write it as e raised to minus 3t integration of e raised to 3t into 10 by 6 into dt. Okay. So again, what is this? This is e raised to minus 3t into e raised to 3t divided by 3 into 10 by 6. So what is this? What is the final answer?
10 by 18.
So it becomes 10 by 6 into 3, that is 18. Okay. So this is 10 by 18. So this is my forced response. So now my total response will be by natural response plus my forced response. Okay. That will be my B1 e raised to minus 3t plus B2 e raised to minus 6t plus 10 upon 18. All right. So that is how you find the complete solution.
Sir, doubt.
Yes, yes, sir.
Instead of doing all this, can we just assume e power 0t in the first step and just substitute 0 in the place of d, right? Can do that, right?
Yeah, that also can be done. That also can be done. So because this is a constant, okay, let me go here. Because this is a constant, I just substitute d as 0 and I can do it.
Yeah.
Yeah. That's a simple way. So once you have solved all this, then you can easily identify how you can do. Okay.
Yes.
So that's a simple way. Then another thing is, so any queries in this or I can proceed? How many of you are there? Kavya is there, Bharat is there, Akash, Amit, Raganapati, Bhavana, all of you guys, any questions? Okay. So let's start solving sums actually. We'll solve sums. So okay, let us consider this sum. Okay. So what are they asking in this sum? They are telling I'm closing the switch and then we have to find the currents I1 of t and I2 of t. Okay. So there is a switch. Because there is a switch, there is a previous there's a previous operating state or previous conditions, initial conditions. So when the switch was open, or t is less than 0, what was my circuit? So my
Only
circuit,
the first part.
yes, only the first part. So it will be this one. It will be this 5 volt over here, this 8 Henry over here, 16 ohm over here, and this is open. Okay, this is open. 4 ohm is over here. So I told you, when you're solving, you must consider the current through your inductor, IL. This is something which is important. Can you tell me what is the current to the inductor in this case in steady state? IL of 0 at 0 minus. What is that value?
Inductor will act as a short circuit.
Sorry?
Inductor will act as a short circuit. Total current.
You're correct. It's true. Inductor will act as a short circuit, but what is the current which is flowing?
So 3.2.
V by R.
It will be 0.3125 if I'm not wrong.
Yeah.
5 by 16. Na? मेरा calculator.
Yeah, V by R 5 by 16.
Okay.
3.125.
Okay, 3.125, yes. 0.3125, no?
Yeah, 0.3125.
Yes. Okay, so this is my current. Okay, ampere. Okay, so all these units are very important because question sometimes if it asks in milliampere and you write as 0.3125, you get it wrong. Okay, so units are important for getting marks. So my inductor current in the at steady state earlier before the switch was closed was 0.3125 ampere. Now when my switch is closed, okay, my switch is closed, t greater than or equal to 0, my circuit becomes okay. Is this clear? This is my inductor current. Okay. Assume this node, okay, this is the same node. I give it some voltage Vx. Okay, I give it some value of voltage Vx. So let us apply KCL over here. Let us apply KCL. We apply KCL at node. What will we get? Okay, what is KCL? It is a current. It is a current flowing into the node, which is equal to current flowing out of the node. So that current which is flowing into this node, that is I into L. Okay,
IL.
IL. And the current which is flowing out of the node is this one and this one. That is Vx upon 16 plus Vx upon 4. Okay. So effectively, what is this equal to? So my IL, I can write it down as 5 by 16 Vx. Is there any doubt in this?
No.
Okay. So I've written my IL is 5 by 16 Vx. Okay. Next, I will write down. Now you apply KVL. You apply KVL in this circuit. What will you get?
Phi equal to
Okay, phi is equal to
8 DIL by dt.
8 DIL by dt.
The resistance can be taken as both the resistance can be converted into a single resistor.
Yeah,
So
that is
both
one
the
method.
voltages are
That is one
Parallel
method.
combination.
That is a method. Or else I can just write it as Vx, right? The voltage across this is Vx. So voltage across this also is Vx, right? And I have found out Vx. I write it down as Vx. Okay. I'm applying KVL over here. 5 volt minus 8, this is 8 DIL by dt, plus the voltage drop across both the resistors. The voltage drop across both the resistors, same Vx. So I write it as Vx.
Got.
Now Vx I know is 5 by 16. So IL is 5 by 16 Vx. So what I do is, instead of Vx, I replace it by IL. So it becomes 8 into DIL by dt plus 16 by 5.
By 5 I.
Yeah, IL. Okay. So I write it further as, okay. So this is 8 DIL by dt plus 16 upon 5 IL is equal to 5. Now it is practice to divide by this 8. So it becomes DIL by dt plus 16 divided by 8 is 2. So this is 2 by 5 IL is equal to 5 by 8. All right. So I have got my differential equation. Okay, I have got my differential equation. Now I have to solve it. So there is one method which I think Bhavna only told of doing
Yes.
d by dx plus py equal to q. There's that method. Okay, that is only applicable for first order differential equations. And this is a first order differential equation. You can apply that method. Okay, but what I'll try to do here is uh, we will use the method which I just showed. Okay. Uh, Sorry for the noise. Okay, there's some noise here. Just bear with me. So I replace d by dt by d. All right, by capital D. So it becomes DIL plus 2 by 5 IL is equal to 5 by 8. Okay. So this I write it as D plus 2 by 5 IL is equal to 5 by 8. And what is my auxiliary equation then?
D plus 2 by 5 is equals to 0.
So D plus 2 by 5 is equal to 0 is my auxiliary equation. So what is this? And so the roots of it are minus 2 by 5. Okay.
Hmm.
So what is the natural response? So IL for the natural part is equal to some constant. Let us assume C1.
V1.
That is e raised to
In
minus
power 2 by 5
t.
t.
Okay. This corresponds to the natural response of the system. Okay. Now we will add the forced response. This is for the natural response. Now I will go for the forced response. So my IL, which is due to the forced response, is this constant 5 by 8. 5 by 8 into 1 upon my auxiliary equation. That is D plus 2 by 5. Okay. So how will we solve this?
I just apply 0, substitute D is equals to 0.
Okay, that is a easy way. Because this is a constant only and it is not a function of t, okay, we can substitute d is equal to 0. Okay, so we substitute d equal to 0, we get 1 upon 2 by 5 into 5 by 8. That comes out to be, so what happens? This 5 goes to the numerator, so it becomes 5 into 5 divided by 2 into 8. So this becomes equal to 25 upon 16. Okay. So don't mess up what goes in the numerator, what goes in the denominator, all those. Sometimes these fundamentals, we make mistakes in them. Okay. That's why I'm writing very slowly. Okay. I just like to point out, okay. So this is the value we get. So what is my entire solution? My entire inductor current is given by IL of the NT plus IL due to the forced response. So this is, what is the natural thing is C1 e raised to minus 2 by 5t. So that is C1 e raised to minus 2 by 5t plus the forced response is 25 by 16. So 25 by 16. So this is my IL of t. Okay. All right.
Yes.
What about others? Bharat,
Yes, I got it.
Amit, Kavya. Okay. So this is what we got. Now we don't know what is C1. How will you find C1?
Initial conditions.
Boundary condition.
So what is the initial condition?
IL of 0 is, what is the value? 5 by 16.
Okay.
IL of 0 minus. Yeah.
So we put substitute t is equal to 0. What will we get? We will get IL of 0 is equal to C1 into e raised to minus 2 by 5 into 0. So 2 by 5 into 0 is 0 and anything raised to 0 is 1. So that's why this becomes C1. And this is 25 by 16. Okay. Now what is your IL of 0? That is 5 by 16. So this is the equation. So we will get it to be of the form C1 is equal to 5 minus 25 by 16. That is minus 20 by 16. That is minus 5 by 4. Or that is actually equal to minus 1.25. Okay.
Yes, actually.
Okay.
Yes, sir.
So now how? So I've got C1. So my IL of t is effectively minus 1.25 e raised to minus 2 by 5 t plus 25 upon 16. Okay. So my IL of t, I write it down further as 25 by 16 is. So what is 25 by 16? Hmm?
1.5625.
So that is equal to 1.5625 minus 1.25 e raised to minus 0.4 t. Okay. So this is the equation for my inductor current.
Yes,
So
sir.
yeah. So this is the equation. So I have gone through so much of trouble, so much of steps. From here, I have spent so much of time. I wrote the differential equation I wrote. Then I found the auxiliary equation I got. Then I found the natural response I got. Then I found the forced response. And because it was a constant here, I could put d equal to 0. So I didn't have to do much of integration. I got the value. This is my forced response. This is my inductor current. So overall, this is the equation. Still, I don't know what is a C1. So I had to use initial condition. And then I got the final equation. Okay, this is the final equation I got. Okay, the meeting will end in 10 minutes. So I'll again start after the meeting ends. Okay. So to solve one circuit, it has taken me so long. Okay. So now what? There is a easier formula actually, which can be applied for this circuit. In this circuit, if you look at the circuit over here, there is just one single inductor. Only a single inductor is there. And you have these resistors, etc. there. So what we can do in this case is there is a formula which can be applied. Okay, for the circuit, for the circuit after the switch is closed, what is the inductor current in steady state? For this circuit, what is the inductor current in steady state?
VL,
Sorry,
IL, right?
this IL. What is IL in steady state?
5/16. Or for the second circuit, if you are done.
Yeah, second circuit. Yeah.
For that, we have to find the equivalent resistance of the circuit and then not the
So there is a easier
or
method.
VX.
Easier method is what? You replace your inductor by a short circuit. If it is a short circuit, what is the voltage at Vx?
Zero, right?
If this is a short circuit, the voltage at Vx will be equal to 5 volt, right?
Yes, sir.
So when this is a short circuit, what will be the equation? What will be this? It will be like this. And this is a short circuit which is due to the inductor, okay? So your inductor is replaced by a short circuit. So this is your Vx. So your Vx is equal to 5 volt, okay? And this is your current which is flowing through your inductor. So you can get your inductor current is actually 5 volt upon 16 plus 5 volt upon 4 ohm. So what will be your inductor current in steady state?
1.5, 1.56.
25. So it is 1.5625 ampere. Okay. Achha. Then, okay. What is your equivalent resistance? Equivalent resistance.
3.2.
Okay. How did you get it?
1/16 plus 1/4.
Then you also do reciprocal of that, right?
Yeah. Like R1, R2 by R1 plus R2. This formula I've used.
Okay. So this will be 16 into 4 by 16 plus 4. This
Yes,
is
64/20.
your resistor. Okay. So that will be, yeah, 64 by 20 to 3.2. So that is 3.2 ohm. Okay. Any queries? Anyone else has queries in R equivalent?
No, sir.
Okay. So all right. So we'll go to next page. So I've got 3.2 ohm is my R equivalent. So my IL of 0 was 5/16, that is 0.3125 ampere. My IL of infinity is 1.5625 ampere. My R equivalent is 3.2 ohm. My L actually is 8 Henry. So I can use this formula. IL of t is equal to IL of infinity plus IL of 0 minus IL of infinity e raised to minus RT by L. There's the shortcut formula. So that will be equal to IL of infinity is 1.5625 plus IL of 0 is 0.3125 minus 1.5625. My R equivalent is 3.2, so 3.2 T upon 8. So that comes equal to 1.5625. What is this? 0.3125 minus 0.5 minus 1.5625. How much is it?
Minus 1.25.
So this is minus 1.25. And what is 3.2 by 8? Hmm?
0.4.
0.4.
This is 0.4 T. So I got the same answer over here also. This is the same. This is the same. This one as well as this one. Okay. So if you know this formula, you can save yourself the time in solving it. Okay. But you must understand in which circuits this can be applied. It cannot be applied to all circuits, etc. So that you will get to know by practice. Right? So this was done. So these are easy when there's only one single inductor or only one single capacitor in the circuit, and using this method is easy. This method becomes easier. Okay. So that is how. Okay, don't worry about notes. So these notes, I will make it into a PDF and I will upload it on my Google Drive. And a link to that Google Drive also I will attach it. Or I forget the attachment link. We'll add. Send it on chat. Okay, and also these videos are recorded, so I will upload it on my YouTube channel. So I'll send these links. So this is the link for the YouTube channel where I'll upload the recordings of this meeting. So you can revisit it if you have any doubts. And this is the drive where I will be uploading these notes, okay, for you to refer. All right. So even though I'm uploading, it doesn't mean that you don't write over here and solve. It is good if you solve simultaneously with me. Okay. That helps you to retain the information. So I have got, so we have solved this sum. All right. Now they have asked us to find I1 of t and I2 of t. So I have got IL of t, I have got. This is my IL of t. Can anyone tell me what is I1 of t then? In terms of IL of
We
t?
can find it using current division rule.
Yes. So by current division rule, I1 of t will be equal to 4 upon 16 plus 4 into IL of t.
IL of t.
What? It is just the resistor next resistor divided by the total resistance. So similarly, I2 of t is equal to 16 divided by
16 into
IL of t.
L of t.
Okay.
That's it.
Yeah. So that way you can easily solve. So that's why I say you must find a current through the inductor. Once you get that, then these things are simple. Okay. Yeah. So this meeting will end now in 1 minute, less than a minute. Then I will again restart the meeting. Okay. Then you can join. Okay, so
Is it the same link that we have to join?
yeah, same link, same link.
Okay. Okay.
So let us consider this case. Okay. This question. What we have is initially the switch was open and at time t equal to 0, the switch is closed. So what was the circuit before the switch was open? Before
Only
that,
the first loop will be considered.
yeah, only the first thing. So can you tell me what will be the voltage across this capacitor?
Twelve volt.
How much?
12 volt.
Yes, it will be 12 volt. Why? Because this is 12 volt. This is your resistor 5 ohm. This is your capacitor. Okay. In steady state, this will act like an open circuit. Open circuit means what? The current over here will be 0. Okay. And this voltage also will be 12 volt. So VC of 0 is 12 volt. So can you tell me how much is the charge stored in this capacitor? This capacitor 4 millifarad. So how much is the charge stored in this capacitor?
Q is equal to VC.
Sorry?
Q equals VC.
VC, right? VC of 0 into C. So what is that? That is equal to 12 into 4 into 10 to the power minus 3.
48 milli.
Milliwatt.
Coulomb.
Coulomb. Coulomb. Yeah, so this is important. The what is the dimension or what is the quantity? Millicoulomb. So this was the initial charge stored on the capacitor. Also, they have written that the capacitor on the right hand side was uncharged. If it was uncharged means VC of 2 at 0 is 0 volt. So let us assume this Q1 and Q2 is what? VC2 of 0 into C2. Since it is 0 volt, the charge stored in the capacitor at
0
Q2
coulombs.
0. So what is the effectively charge stored in the system? Effective charge is Q1 plus Q2. That is equal to 48 millicoulomb. All right. So we have found a charge stored on the first capacitor, and the second capacitor was uncharged, didn't have any charge, and the voltage across it was 0. So the charge is 0. Now, what happens is suddenly the switch is closed. At time t equals 0, the switch is closed. So my new circuit will be like this. It will be of this form. 12 volt, 5 ohm, 4 millifarad. And what is the other capacitance? 10 millifarad. Okay. So what is my effective capacitance? C effective now.
C1 plus C2. 14 millifarad.
14 milli.
14 milli.
C1 plus C2. What is my effective charge? Okay, so my charge cannot immediately change. At time t equal to 0, my charge cannot immediately change. So my charge will remain as 48 millicoulomb. So now I want to find what is my effective voltage over here. My effective voltage over here will be equal to the Q effective upon C effective. That is 48 millicoulomb upon 14 millifarad. And what is that value?
.42.
Okay. So that will be 3.4285 volt. Okay. So now in this circuit, at time t equal to 0, at time t equal to 0, my effective voltage across both the capacitors is 3.4285 volt. Okay. So here is the confusion. This is what even I got confused. We usually consider that the voltage across the capacitor cannot change instantaneously. Okay, but actually it is just the charge which is stored in the capacitor cannot change instantaneously. So initially the voltage across this capacitor 1 was 12 volt. It was 12 volt, we established it is 12 volt. But just when you close the switch, what happens is the charge gets redistributed, the charges gets redistributed, and the effective voltage becomes 3.4285 volt. This is confusing, but try to understand. Okay. So what have we got? We have got the initial voltage now is 3.4285 volt. Now in this circuit, you tell me what will be the final voltage across the capacitor. Final voltage means the steady state voltage across the capacitors.
Capacitors act as open circuit.
Yes, so if it acts as an open circuit, what will be the voltage across it? So when it,
Zero.
no, it acts as an open circuit means what? If you see open
12
circuit,
volts.
yes, 12 volt. Let me just explain. So this is 12 volt. This is 5 ohm. And this is an open circuit. Okay. It's an open circuit. Assume it's an open circuit. No, it is open. Okay, but this is just assume. So open circuit means what? This current over here will be 0. Now what is this voltage over here? I cannot say it is 0. It must satisfy KVL. So when I apply KVL in this loop, it will be 12 minus 5 into 0. 5 into 0 plus this voltage V. Okay, so it will be is equal to this voltage V. So my voltage V, because it is current is 0, because it is open circuit, current cannot flow. So my voltage V will be 12 volt. Okay. If there is any voltage difference across the resistor, current will flow. Now, because it is open circuit, there is no current flowing. And if there is no current flowing, that means my voltage V has to be 12 volt. All right.
Yes, sir.
So we have established that the voltage V is equal to 12 volt. So this is my final voltage. The final voltage is 12 volt. All right. Now, as we have done for the inductor, we have found a generalized equation. We can apply that equation. We say V of t is equal to V of infinity plus the bracket V of 0 minus
0
V
minus t of infinity
e raised to
into
minus
e power minus t by RC.
R into C effective. So that becomes 12 plus 3.4285 minus 12 into e raised to minus t by R is 5. C effective is 14 millifarad. So that is 14 into 10 to the power minus 3. That becomes what? So what is 3.4285 minus 12?
Minus 8.5715.
It becomes minus 8.5715 into e raised to what?
Is to
70 into 10 to the power minus.
70 into 10 power minus 3.
Sorry? Oh, 5 into 14 is 70 into 10 to the power minus 3. Okay. So I want it in a numerator. So it becomes actually e raised to minus 14.285. Okay.
Yes, yes.
Okay. Yes. So this is how we have solved. All right. So I'll go through it over again. So there was one initial condition and we found some initial voltage and we found what was the charge stored in the system. Then the switch is closed and the charges get redistributed. Okay, it gets redistributed. Some charges come here, some charges come here, etc. So when the switch gets closed, some charges comes here, some charges come over here. the effective charge will not change. So the voltage now changes, and that voltage is this. And then we solve it at final in steady state. This is open circuit. Open circuit means no current flows here. That means this voltage also has to be 12 volt. And then I use this shortcut formula and I get my answer. Okay. So we will solve one final sum. Also, do you guys know this cool thing actually? You can also get a text if you take a snapshot. If you do it, you can get this text also you can take and you can copy it. So this might be useful for writing your reports, everything. Okay. Okay, so if you have an image or if you have an assignment also, you can do it this way. Okay, so this is a question. So there's this circuit is there, and we have to solve it. Okay, we have to find the current through the inductor and the voltage across the capacitor. So what do? We consider incident before the above circuit was in steady state and the capacitor was uncharged. The capacitor was uncharged means the V of 0 is 0 volt. And what is your current, inductor current in steady state when the switch was open? Is how much?
IT.
Sorry?
Short circuit current, I of T.
I of how much is it?
$240 by 20.
It is 240 by 20.
12.
That is
12.
ampere. Okay. Now the switch is closed. So my circuit becomes like this. Comes like this, 10 Henry. Okay, this is my circuit. So how do I solve it? Now there's no shortcut formula which I can apply here. Okay, there are two energy storing elements. So what I have to do is I have to apply KVL and KCL. So first let us apply KVL or let us apply KCL. So when you apply KCL, you will apply at this node. Okay. And what is the voltage at that node? That is V of t is the voltage at that node. So can anyone tell me what will be the KCL of it? Okay, Kavya, you're not answering. Bharat, Raila Suresh, Raja Ganpati. Okay. So we apply KCL. That is the current flowing into the node. I of t is equal to current flowing out of the node. Now, what is the voltage across at here? It is V of t, right? Voltage at this node is V of t. So that's why the current flowing out is V of t divided by 20. This I've got. Now, what is the current flowing in the capacitor? The current flowing in the capacitor, as you guys know, is C into dVC by dt.
By dt. Yeah.
Yeah. So that will be 1 by 180
180 into
d by.
dVC by.
Okay. So this is my equation 1. I got my first equation. Now, let me apply KVL. Okay, I'll apply KVL. So I apply KVL. I apply KVL over here. Okay. What I will get? Now tell me. Suresh, Ranjit.
Minus 240 plus L
Okay,
into
minus plus
240 plus 10 into di by
10.
dt
Okay.
plus 20
Plus
into
20 into.
so I1 minus I2.
Okay. So here you can write it as I of t minus IC of t. That is one
Okay.
way. But there is an easier way. What actually is the voltage? See, V of t is a voltage across the capacitor, right? That same voltage is the voltage across your resistor as well. The resistor and your capacitor are connected in parallel. So the voltage across the capacitor is the voltage across your resistor. And this drop across the resistor is the voltage across the resistor. So instead of writing it in this form, I write it simply as V of t. Because it is the same. So I'll repeat it.
Yes.
So I found
Yes, sir.
voltage is 240 plus 10 di dt plus this drop across this resistor, that is the equal to the resistance into the current. But I have a better way, easier way, is I know the voltage across the the capacitor and resistor are in parallel. So the voltage across the resistor is the voltage across the capacitor. Okay. So that I have done is simple, easy for me. So I write my final equation as minus 240 plus 10 di by dt plus V of t is equal to 0. All right.
Yes, sir.
I write it further as 10 di by dt plus V of t is equal to 240. Right. Now, what I do is I substitute I of t. So this is my equation 2. This is my equation 2. Now I substitute I of t in this equation over here. So I get V of t, I'll leave it as it is, plus 10 into d of dt into I. What is my I? This. So my I is V of t upon 20 plus 1 by 180 into dV by dt is equal to 240. Okay. So what I do?
Yeah.
I add new page. So it becomes V of t plus dV by, so 10 upon 20 into dV of dt, derivative of V, plus 10 upon 180 into the second derivative of V, d2V upon d2t is equal to 240. Okay. So this becomes equal to V of t plus half dV by dt plus 1 by 18 into d2V upon d2t is equal to 240. Okay. So I write it further as d2V upon d2t. I multiply throughout by 18. So this becomes 18 upon 2 into dV by dt plus 18 into V of t is equal to 240 into 18. Okay.
Okay, sir.
So this becomes d2V upon d2t plus 9 into dV by dt plus 18 into v of t is equal to, what is 240 into 18?
4320.
4320. So now I've got v of t, right? Now I replace d of dt by my operator d. So I will get d2v plus 9dv plus 18v is equal to 4320. So I get d2 plus 9d plus 18 into v is equal to 4320. Okay. So what is my auxiliary equation?
D square plus 9d plus 18 equals to 0.
That is d square plus 9d plus 18 equal to 0. So that comes out to be d plus 3 into d plus 6 equal to 0. So that is d is equal to minus 3 comma minus 6. So you get your natural response, v natural response is some c1 e raised to minus 3t plus c2 e raised to minus 6t. All right.
Yes, sir.
Yes, sir.
Now, further we can write, now we have to find the forced response. So my forced response is what? Vf of t is equal to 1 upon d plus 3 into d plus 6 into 4320. Now we have the shortcut, we put d equal to 0. So we get it as 1 by 3 into 6 into 4320. That is equal to what?
240.
240. So this comes out to be 240. So my final equation of v of t is equal to c1 e raised to minus 3t plus c2 e raised to minus 6t plus 2 for t. Okay. This is my vt. So this is equation 3. Now I know from equation 1, my I of t is v of t by 20 plus 1 by 180 into dv of dt. So I will apply it. So my I of t is v of t by 20 plus 1 by 180 into dv by dt. So that will be c1 upon 20 e raised to minus 3t plus c2 upon 20 e raised to minus 6t plus 240 upon 20 will be 12 plus, okay, 1 by 180 d of dt of c1 e raised to minus 3t plus c2 e raised to minus 6t plus 240. So what does that become? So we write it as I of t is equal to c1 upon 20 e raised to minus 3t plus c2 upon 20 e raised to minus 6t plus 12. What is the derivative of e raised to minus 3t?
Minus 3 e power minus 3.
So it becomes minus 3 by 180 minus 3 by 180 c1 e raised to
C1
minus. Then it becomes minus 6 by 180 c2 e raised to minus 6t and derivative of constant is 0. Okay?
0.
So I get it of the form I of t is equal to, I take c1 and e raised to minus 3t common. I will get it as 1 by 20 minus 3 by 180 plus c2 into e raised to minus 60 common. So this is 1 by 20 minus 6 by 180 plus 12. So my I of t is equal to, so what is 1 by 20 minus 3 by 180?
0.033.
So it is by 30. Okay, you can do it. Plus C2 e raised to minus 6t. What is 6 by 180 into minus 1 plus 1 by 20. So this is into 1 by 60. 1 by 60 plus 12. Okay, so you have got I of t. You have got, this is equation 4. Okay. Any doubts in this?
No.
So what we do is, now, but we don't know what is C1, we don't know what is C2. Even in the voltage equation V of t, we have C1 and C2, but we don't know what are their values. So how we solve it is, I put substitute t equal to 0, I put. What is V of 0? V of 0 is equal to 0. V of 0 is equal to 0 and I of 0 is 12. So we write that V of 0 is equal to 0. That means 0 is equal to, what is V of t? C1. What is e raised to minus 3, 0?
1.
Yes. So this will be C1 plus C2 plus 240. So this will be 0 is equal to C1 plus C2 plus 240. This is equation 5. Similarly, if I put t equal to 0 over here and I of 0 is 12, so I will get 12 is equal to
12 equal to
C1 upon
1 plus
30
3
plus C2
plus
upon 60 plus 12.
plus 12.
Okay. So what can we do now? We can cancel 12 and 12 get cancelled. So we get 0 is equal to C1 upon 30 plus C2 upon 60. That we can write as 2C1 plus C2 upon 60. Is it fine?
C2 equal to minus 2C1.
Okay, so we get C2 is equal to minus 2C1. That we substitute over here. So we get, what do we get? C1 plus C2 plus 240 is equal to 0. So we put C2 is equal to minus 2C1. So we get C1 minus 2C1 plus 240 is equal to 0. So minus C1 plus 240 is equal to 0.
C1 equal to 240.
So C1 is equal to 240 and your C2 is equal to minus 480.
Minus 480.
Okay. So you substitute this in your V of t and in your I of t, you will get. Okay. So if you put, we get V of t is equal to, let me go back. So C1 e raised to minus 3t. Okay. So it is 240 plus 240 e raised to minus 3t minus 480 into e raised to minus 60, and I of t is equal to 12. Okay, 12. I of t is 12 plus C1 upon 30. What is C1 upon 30? What is C1? What is 240 upon 30?
8.
So that will be 8 into e raised to minus 3t. And what is C2 upon 60? And C2 is minus 480. So that will be equal to what? Minus 480 divided by 60 is how much?
Minus 4.
No, minus 480 divided by 60.
Minus.
Yes, so it will be minus 8 into e raised to minus 6.
Yeah, minus 8.
Okay. Okay. So in this manner, you have solved a second order differential equation. You have used the initial conditions and you have applied it for a second order circuit. So any doubts in this?
No,
Okay. What about Bhavna, Akash, Mohandas,
Yes, sir.
Sabari? Yeah. Okay. So I'll do a recap. So first, we found out that there will be differential equations in electrical circuit because of your energy storage elements, your inductor and your capacitor. Then we saw for a first order circuit, we found KVL, and then I told that it is better to write the equation in terms of the voltage across the capacitor and the current through the inductor. All right. And then we saw that the order of differential equation is equal to the number of energy storing elements. Then for a second order system also we considered that. And then we try to understand a way to solve these linear differential equations. Okay. So this d by dt is replaced by the operator d. And then you get it in terms of an algebraic equation. Okay. And this algebraic equation is your auxiliary equation. So that is your auxiliary equation. And you solve that auxiliary equation and you will get the roots of that auxiliary equation. And then you will write this solution. This solution is known as a natural response. Okay. So this b1 e raised to minus 3t plus b2 e raised to minus 6t. We just considered some random values. Then we considered, and this was the case when this is 0. But in case it is not 0, there's an additional solution. You will have your natural response will be there, plus you'll have a forced response. So the natural response will still be there. That is the same as we calculated in the previous steps. But there will also be a forced response. And to solve that forced response, we solve it using this method. Okay, this method we use to solve the forced response. We consider one example and we solved it and we got the solution to be of this form. And we realized that if we substitute d equal to 0 also, we will get the same form. Because this was a constant. So it was applicable. Okay. Then we got whatever mathematical tools, whatever ways we must solve, we have understood. And then we started solving these equations. So again, in this case, you find the initial condition. You solve it for the inductor current. Once you get the inductor current, then you solve for I1t and I2 of t, which is simple by current division. Okay. Then we go to the next case, question 2, where there are two capacitors. So initially the capacitor is charged to 12 volt because it acts as an open circuit. Then when you close, and then we found out what is the charge, overall charge stored in the system. So there was some 48 millifarad, some charge stored. Similarly, there was no charge. So the overall charge stored in the system was 48 millifarad. Now I close the switch at t equal to 0. So because when I close the switch at t equal to 0, what happens? The charges get distributed. So the charges gets distributed. Some charge goes over here. So when the charges gets distributed, the effective voltage comes out to be 3.4285 volt. Okay, I get that effective voltage. Then also we had found out a shortcut method. So I find a final value of the capacitor voltage, that is 12 volt. Okay, once I get that, then I use this technique. I use V of infinity plus V of 0 minus V of infinity into e raised to minus t upon RC effective. I use this method and then I get this equation and then I get the solution. Okay. Similarly, in the last sum, we are RLC. We found the initial conditions. Then here, in this case, we cannot use such simple methods. Simple methods are here is not applicable. So we had to write each and every equation. We applied KCL, we applied KVL, and when I applied KCL, I made sure that I wrote in terms of my capacitor voltage. I solved it in terms of my capacitor voltage. Okay. I also applied KVL, also I applied. And then we did simplification. We solved the differential equations. We got V of t, we got I of t. We applied the initial conditions and got these C1, C2 and all. We found their values and then we finally got these expressions. Okay. Yeah. So that was for today. So if you have any other queries, you can ask. Mohandas, Sabari, Bharat, Kavya, Bhavana, Akash, Suresh. No
Not
question.
related to subject, but
Mhm.
the
No
session will
doubts
be
as of
always
now.
on Tuesday, right?
Sorry?
This session will always be on Tuesdays, right?
Yeah, it will be on Tuesdays. Yeah, 6 to 8.
Yeah, that was.
Yeah. Then Bhavana, you're saying something?
No, I don't have any doubts as of now. Thank you so much
Okay.
for your session.
Okay. So this
Yeah, thanks a lot.
yeah, welcome. Thank you. So it was good that it was a bit interactive. Some of you were answering. So when you answer, I'll get some sort of feedback real time. Okay. So these videos I will upload on YouTube. Also, these notes also I will upload on my Google Drive. I have shared that those links on in the chat, so you can access that. Okay. All right. So I'll end the meeting. So this is enough for today. Okay.
Okay,
Yes,
thank
sir.
you.
Thanks.
Okay, sir. Thank you.
Good night. Bye.